Okay, let's begin talking about Chapter 2, Systems of Linear Equations. As an overview, the theme here is a method called Gaussian Elimination. That's the main theme of this chapter. And we're addressing systems of linear equations. We'll write them as matrix equations. And Gaussian elimination is an efficient algorithm or procedure for simplifying a system of linear equations or matrix equation so that it can be solved. All right, so those two main subjects, linear equations and Gaussian elimination, applied to linear equations to solve them. All right, well, section 2.1.1 delineates the connection between systems of linear equations and matrices. In other words, given a system of linear equations, it associates a matrix. And the matrix it associates is called the augmented matrix. So the augmented matrix for a system of linear equations is the matrix corresponding to the linear function concatenated on the right with the vector output. So let's go take a look at this example. Here's our original system of linear equations. The matrix corresponding to the linear function comes from the coefficients of these variables here. So that's this 1, 1, 2, minus 1, 1, 1, 2, minus 1. So that's the matrix from the linear equation. And then here's the vector of constants, 2 and 27 and 0. And you draw a line, and then you put the two constants. So this is the augmented matrix corresponding to this system. Now, just scroll down, you'll see several examples of the same thing. Right. Here's another example. System of linear equations. The matrix corresponding to the linear function consists of the coefficients of the variables. So for instance, this first line, 1, 3, 2, 0. Here you would have again 1, 3, 2, 0. So that gives this matrix to the left of the bar, and to the right of the bar, you have the constants 9, 0, 3. In fact, there are three ways of representing a linear system. Here you have the original system with the variables. Here you write it as a matrix vector equation, where the linear function is expressed as a matrix times a vector, and the constants are expressed as a constant vector. And then this is further compressed into the augmented matrix. So you can see the augmented matrix is the least amount of writing, so that's the one we use in practical computations. It's also easiest to put into the computer. It's hard to put an X into the computer, but you can simply put numbers into the computer. So that's the convenient form to work with when we're actually trying to solve. And here we see our first example of Gaussian elimination. The steps are not systematically described in the text, but you can see that the system of equations is becoming simpler and simpler. So here he's executing the Gaussian elimination on the system of linear equations and representing it three different ways. This representation, the equation representation, this equation matrix vector representation, this equation augmented matrix representation. Notice each step what he's doing is he is replacing equations in the system with what you could call a linear combination of the equations. For instance, here he says the first equation is replaced by the sum of the two equations. And this does not change the set of solutions, but it does make the matrix easier. The more zeros in the matrix, the better. In particular, the more zeros in the matrix to the left of the bar, the better. And we'll see why that's true. So you see here he put a 0 here. He's going to put another 0 down here. Now notice at this stage that we have a system of equations. X equals 9 minus y equals minus 18. Of course we can change that to x equals y equals 18, and that's my solution. So when I get it down to this form, when you see an augmented matrix of this form where you have what's so-called identity matrix here, then it's easy to read off this solution. You should practice or think about how you can translate back from augmented matrix to system of equations because the augmented matrix is what you're going to work with, but the system of equations is what you want to actually solve. So again, if I have an augmented matrix of this form, remember what this means in terms of variables. This 1 here means the x because the first column corresponds to the variable x. So this is x equals 9. Second column corresponds to the variable y, and this is y equals 18. Right? So as he points out here, the strategy was to eliminate y from the first equation and then eliminate x from the second. And Gaussian elimination is a systematic way of doing this. Now, in this step-by-step procedure, it was important that as we go from step to step, the new system of equations has the same solution as the old system. So if we focus on these augmented matrices, these matrices all represent the same solution set, even though the equations they represent look different. So these are called equivalent matrices. And equivalent matrices are obtained by this process of equation manipulation, which comes down to operations on the rows of the matrix. When I take this first equation and add it to when I take this first equation divided by 3, that amounts to taking this first row here and dividing it by 3. When I replace the second equation by the second equation minus 2 times the first equation, that amounts to taking this second row and subtracting 2 times the first row. So, two augmented matrices are called equivalent if they represent systems of equations with the same solutions, and the process of Gaussian elimination can be represented as a sequence of equivalent augmented matrices. Another example is example 12 on page 40. There are several examples of the process of Gaussian elimination. So let's see if we can understand what he's doing here. Here is the original system of equations. Here is the augmented matrix. You can see here's 1, 1, 1, 2, 1, 1, 1, 2. Here's 5, 8. Here's 5, 8. All right, now how did he get from here to here? Notice that he made this variable here, this 1 here, he made it a 0. This one he kept the same. This one he made it into a 0. So we'll see that what you do when you do Gaussian elimination is you work on the first column first. So you got a 0 here by subtracting the first equation from the second equation. You can see that. Take the second equation minus the first equation and you get this second row here. Right? So that doesn't change the solution set, but it does put a nice 0 here. And if you think about the equation that this row represents, it represents y equals 3. Very nice. I know what y is now. Right now, to go from here to here, what did he do? Well, he took the first equation and subtracted the second equation and replaced that in the first row. So first row minus second row, and replaced it in the first row, and you get 1, 0, 2. All right, now this first row now represents x equals 2. We have our solution. So notice it was a process of removing non-zero entries from the first column and then removing non-zero entries from the second column. Okay. So this 1 here is the only non-zero entry in this column. This 1 here is the only non-zero entry in this column. These two entries are called pivots. Right? So the process of Gaussian elimination is the process of creating pivots. Every time you have a pivot, that makes it easy to find a certain variable. All right? So we'll see more about that later on.